Hello, greetings. My name is Chris. I will be presenting my final course project for Machine Learning Foundations for Product Managers via Coursera in relation with Duke University. Here are just some general guidelines for the approach of the course project, which highlights the model approach, the different logarithms that are used, and the evaluation of the performance of my final model. The goal of this project will be to build the goal of this project will build a model to predict the electrical energy output of a combined cycle power plant. The data that was provided to us was used for sensors at the power plant that we were going to use in our model. The total observations for this is 9,568. The type of logarithm that we're going to be using is supervised learning. And I will be doing the analysis on two different models, both using linear regression, one with a single feature value and one with a multi-set feature value. Our test data split will be 80-20, so 80% representing training data and 20% representing test data. And then later on, our evaluation will be conducted using these metrics here below. My approach for this was with Excel. So you can see here that my training data was split in that 80-20, 80% test training set and 20% test set. Below here just shows an overall view of what our features are and the type of models that we're going to use and an output of what our split is for our training and test data. The first model, linear regression for a single feature, we're using that 80% model for the training data. For my feature, I chose ambient temperature to evaluate. And so we can see here in my when I ran the regression model, I get an output of regression statistics, as well as I get the intercept value coefficient, which is the target value PE, and then our X variable, which is our feature ambient model that we ran. Here just shows a output of these values and metrics, and each one of them gives a description on what those metrics are trying to tell us in relation to the value. Our Model 2 linear regression for multiple features uses the same approach, 80% of the training data. The only difference is instead of using just ambient temperature, we're using all features. Here just shows a breakdown of the target value PE, our regression statistics similar to Model 1, and then our coefficients that we will need to use in our later model evaluation. The intercept representing the target value PE and our X variables representing the features that we used. This shows the model output statistics for that Model 2 linear regression. Again, shows the metric and the value that was used and a description of what that metric is trying to tell us. This is a Model 1 and 2 output comparison between my Model 1 using that single value of ambient temperature and Model 2 value using all features. So we can see that the model outputs are very similar, but what we're looking for in the first three here is a higher value closer to 1. The model and the accuracy evaluates in binary values 0 to 1, meaning that closer to 1 for these particular matrix indicates a higher form of accuracy, with 0 being less accurate. So for our Model 1 evaluation and test, in this case we use our 20% of our test data. We ran it with the Model 1 comparison with a single feature of ambient temperature. And based off of the regression statistics, we needed to grab and use the intercept coefficient, that predicted value, and also that X variable coefficient as well. And for this model, we're trying to determine the accuracy of our target value output versus the predicted value that was already included in our training set. The metrics that we use to evaluate the model are indicated here below, which I'll go over in the next few slides. And this screenshot just shows you the calculation and the coefficient that was used for that intercept, which is the basis to get to the multiple metrics that we need for evaluation. So our Model 1 evaluation and test indicated our mean squared error, our root mean squared error, our mean absolute percentage error, and our R squared. Our outputs, my outputs based off the calculations I use in Excel, and a description, again, what those values or what those metrics are trying to indicate to us. Our Model 2 evaluation represents the same type of approach. In this case, we're using all features instead of our one feature, ambient temperature. And again, we're taking that intercept coefficient from our regression statistics and using this formula here as the basis to get us to our multiple metric calculations. This just shows the test results from that Model 2 and the output that I was able to get from the calculations that I did for each metric, and again, a description of what those values are trying to tell us. Here's a Model 2 or Model 1 and 2 evaluation and comparison between the two based on my calculations. So we can see that the comparison is very similar in values. But when we're calculating each one of these, they represent a different metric. So in this case, for mean squared error, Model 2 shows a lower average squared error result, which was how we calculated it. And so for this particular metric, we're looking for a lower number, better for accuracy. Our root mean squared error for Model 2 shows a closer prediction to actual values. So 4.77% of the time we are getting closer to that predicted or that target value is a lot closer to that predicted value than a 5.77. For our mean absolute percentage error, this is calculated for the average prediction error, and we can see that it's lower than Model 1. And again, for this particular metric, we're looking for a lower number, the better for accuracy. R squared shows us Model 2 was higher for our variance percentage. So our variance percentage, we're trying to get to closer to 1. And this indicates that this particular model is accounting for more errors than the Model 1. So if I look at our model comparison, our Model 2 performs significantly better across all metrics. Accounts for more variance and lower errors, and Model 2 predictions seem to be more accurate and consistent. Here just shows a scatter plot between the predicted value, which is represented in orange, and the target value output of that one single feature, a nice linear relationship down below those predicted values. Model 2 again shows the predicted values here in yellow, but since we used all of our features for this particular model, we can see all those different scatter plot points here, and I think this is a really good indication of being able to interpret the data a little bit better in more of a visual context, and being able to use more of our features gave us a better indication of the accuracy, which is represented here. So more features gave us a better predicted value. So in conclusion, based off the guidelines that I had on slide 2, I just wanted to call out how I was able to get to that. So first, we needed to choose a machine learning approach. We used our regression, which predicted the continuous energy output value of the power plant. We selected our features and logarithms, being linear regression, single feature, and multi-feature power plant data. We did our 80-20 training and test split. And then we compared our Model 1 with our single feature regression and Model 2 feature regression. And then we used our mean squared error, root mean squared error, mean absolute percentage error, and R squared in our final evaluation to determine the accuracy of our predicted electrical output versus the actual predicted energy output, predicted value. Thank you for taking the time to listen into my project. Hope you have a great day.